Amanda, and Kristian. So the title of this presentation is Search and Rescue Robotics, which is quite a broad title. We will not be able to cover the whole subject today. Instead, we mean to highlight what has been done so far and what might come in the future in a way that can be connected to complexity. And the layout of the presentation will be as follows. I will start with a short introduction, and then Amanda will talk about how search and rescue robots work today and current problems. And then Kristian will talk about what may come in the future, how things can be developed. And in the end, I will give a short summary of what has been said today. Okay, so technology is constantly evolving. I remember when I was a child watching movies like Terminator and Robocop, and I thought that these kind of robots were only a couple of years away. I think we'll have to wait some time before we have Terminators walking the streets. But robots are today already a part of society, especially in the industry. Will probably be more so in the future. Just take quadrocopters as an example. For a couple of years ago, no one knew what it was. Now you can see them pretty much anywhere. So with better technology comes broader areas where you can apply robotics. And one of these areas is search and rescue robotics. In search and rescue robotics, the plan is to use robots instead of humans in the search and rescue operations after, for example, a natural disaster, where it might be unfit for humans to walk around, like after an earthquake in a collapsed building. If you walk around in the rubble and try to find people, the building might collapse more and damage both the rescuer and the rescuee. And highly radiated areas is another example of areas that are unfit for humans. And both in Chernobyl and in Fukushima, robots were used to some extent. And according to the book Disaster Robotics by Robin Murphy, I will come back to that book in the summary in the end. Search and rescue robots have been used 29 times as of 2014. This might sound like a quite small number, but it's partly because it's a quite new science, but also because the nature of these situations. You can't just bring a robot to a disaster site and expect to be allowed in and play around with robots. It really puts some pressure on the quality of the robots. Now it is clear that one would not use the same robot for example handling nuclear waste as for handling a baby. So there are different purposes to these robots. There are these kind of more hands-on robots. There's a clip on YouTube with a set of swarm bots dragging a small child on the ground. The child looks very awkward and doesn't really know what's going on. But there are also robots focusing more on searching and mapping. You could take, for example, a swarm of quadrocopters mapping a large three-dimensional area, and then humans can come in and help the found persons. There's a problem on how to operate these robots. The most intuitive way is to have someone directly controlling each robot. But if you have a swarm, this could be quite hard. So a natural way is to introduce autonomousness. But with autonomousness comes different problems. They might be good for going around by themselves, searching, mapping. But what happens if they encounter a human? Are they hurt? Are they in panic? Are they even alive? These are questions that are quite hard for a robot to answer, but can be a lot easier for humans. And if they should move a person, they will probably need to work together with these robots. And so how they interact with each other and how they interact with humans is one way complexity comes in to SNR. This concludes the introduction, and I hand over to Anna.
Yes, thank you, Erik, for the introduction. And now I will talk about some of the work that has been done in the field of search and rescue robotics. To make the subject easier to approach, we have divided it into 3 subjects, or tasks, if you will. The first task is how to tackle obstacles and traverse complex environments. And the second task is to enable interaction between humans and robots. And the third task is efficient exploration, which is important because without the ability to efficiently explore an area, the robots won't be useful for search and rescue tasks. So we'll start off with tackling obstacles. And how to tackle obstacles is really a question of how to design the robots. There have been many approaches have been made, and a lot of them are inspired by animals. An example of this is the snake robot, as you see in the picture. And instead of using wheels or caterpillar tracks like many conventional robots do, the snake robot uses many interconnected joints, so it can form a snake-like movement and wiggle itself through the environment. Due to its flexible movement and small size, the snake robot can easily traverse collapsed structure and enter small, tight spaces. And this has proved to be very useful in search and rescue tasks because when you enter a collapsed building, you don't need to clear the area to send in humans, but you can send in the snake through a small hole, and then the snake can map the inside and see if there are any live humans inside, which will greatly speed up the procedure. Then we come to the next task, which is human-robot interaction. And there are many aspects of human-robot interaction, but in this presentation we will just consider the interaction between a robot and the human who operates the robot. If the robot is solely operated by a human, a well-designed interface is crucial. To determine important features of such an interface, a study was made during the Rescue Robot competition in Robotics in the year 2003. And in this competition, teams of humans and robots were to tackle three increasingly difficult arenas that resembled a collapsed office structure with dummy victims placed inside. On the easier arenas, the victims were clearly visible and there wasn't very much rubble, like there was some overturned chairs and so on. But in the more difficult arenas, there were more rubble and the victims were partly covered. So in order to evaluate the performance, those who made the study considered so-called critical incidents. A critical incident was if the robot harmed the victim, or if it harmed itself, or maybe if it harmed the environment. So those teams who performed best were those that had the least number of critical incidents. So the results were that important features to have in the interface was a reference frame, and that is some kind of camera output in the interface that shows the robot's position relative to the environment. That will help the operator. That will help the operator not to run into a wall with the robot, etc. Another important feature is a health indicator. So if the robot is somehow damaged and will malfunction, the user can know why it doesn't work the way it was intended. And third part is that if the robot is solely operated by a human, it needs to output all the sensory information that it collects so that the user can evaluate the environment. But this can be quite a difficult task because when you're presented with very much data, it's hard to see what is important. So therefore, they concluded from this study that some kind of automatic representation of important information would be desirable. Like, for example, if the robot detects something that has very high heat levels and may be a fire, the user should somehow be alerted. But such a feature can be hard to implement, and their autonomy comes into the picture. And autonomy can help relieve the cognitive load on the operator so that it doesn't have to evaluate all information. That might be hard for one robot, but imagine controlling a lot of robots. That wouldn't be possible without some degree of autonomy. It has also been shown in another study of this degree of autonomousness that in semi-autonomous robots, They perform best when the robot is in charge of navigation, so that the operator can focus on the search and rescue tasks like evaluating the objects that the robot finds, etc. So now we come to the third task, which is efficient exploration. And as I just mentioned, a semi-autonomous robot performs best when it's in charge of navigation, and it's therefore desirable that the robot can plan its path to a specified target. And one can also imagine a situation where the robot loses connection with the operator and needs to get back so they can fix the robot. Then we want the robot to autonomously navigate its way back home. So in the picture we see a robot that was part in a path planning project, and it's climbing a staircase, and it does so autonomously. This robot uses a laser detector to map the environment, and then it doesn't fully attempt to reconstruct the environment because that would require a lot of processing power. But it uses a process which I won't go into detail about, but it's called lazy tensor voting. So that process makes it able to assess the traversability of the objects. So using this method, the robot is able to climb stairs. Besides path planning, cooperation is also a key feature in efficient exploration. Like if you have many robots or a team of robots and humans, you want them to be able to efficiently explore an area. And I will show an example of this in this picture. I don't know how well you see, but here we have a team of 3 robots and 1 human. And their task is just to explore this area efficiently. So we can assume that the robots have access to the blueprints of the area, and that they also have access to the position of the human and the position of the other robots. So what they do is that first they wait for the human, which is the red dot here. You see in the top right picture that the robots wait for the human to make a move first. So the human chooses one of the upper paths. And I should say also that they begin, since they have the blueprints, they begin with calculating trajectories that if all trajectories are followed, the entire area would be explored. So then they can see that the human chooses one of the above, and then one robot follows the human, so it can take whichever path not followed by the human, and the other 2 robots take the 2 paths that are left. So what is the advantages of such a setup? That is that the human doesn't need to operate all 3 robots. It can just go along and perform its task, and the robots will help. And the robots don't need to completely understand why the human makes his or her decisions. So now I've talked about 3 different topics that have been researched in this field, and one might ask, how well does this work? Well, navigation, as we see, works very well, but it works best in static environments, because when things start to change, it gets challenging, because then you need to make a lot of computations, and that might require a lot of processing power. So that's still a challenge. And we also know that to have fully autonomous robots in search and rescue tasks won't be realistic, because for example, after an earthquake, it can be hard even for humans to recognize victims in dust and rubble. So now Kristian will talk about the future of search and rescue robots.
Thank you, Madam. So we've heard a bit about what's been done already. But what might be of greater interest is what the next step is, and what you might find yourself developing one day. So first we will look at some general navigation of the robots. Next we will dive into the human-robot interaction. And finally, we will look a bit at the optimization and efficiency of the robots. So, without further ado, let's get going. Now, we've heard a bit about the snakes wiggling their way through tiny crevices, mapping out areas, finding victims. But how can this be improved even better? Let's consider a core point in tackling obstacles and navigation for the search and rescue robots. It's not just for the robots to find their own way through the area, but also to find a relatively safe way for the human rescue personnel. Now, what this requires in the robot is an intelligent design in their analytical systems, such as the sensor data gathered and how this data is handled. So, how do we improve upon this? Well, a good first step would be for the robots to gather this data and recommend actions for the operator on how to proceed. The robots might read from their environment, find some different paths, and notice that, oh, this path seems safe for humans. Then it will send a message back to the operator and say, okay, this path is safe, you should choose this path. Now, in the case of mapping for human personnel, how would the robot go about choosing this path? Well, of course, it requires sophisticated mapping abilities. And through some rough simplifications, we boil it down to two options: quality or quantity. So either we have the quantity solution with a multitude of small robots swarming in, and basically mapping out by trial and error. So a robot might fly into a fire and just crash, but before it goes out completely, it might send back a message to the operator and be like, oh, this fire killed me, you might not want to send people this way. And another solution will instead be quality, where a robot is packed with sophisticated sensors, goes into an area, maps it out all on its own, and then suggests the appropriate route to the operator. And of course, the idea here is that the quality robot would not go sacrificing itself, since that would be way too expensive. But what I'll be focusing on here is the quantity solution, the multiple smaller robots swarming in. Now, in order to address this issue, it's vital to analyze the human-robot interaction. As previously mentioned, these operations place an enormous cognitive stress on the robot operators. Now, imagine that stress multiplied 20 times as you try to control 20 robots in a swarm. So, it's vital to reduce this stress and allow the operator to focus solely on the search and rescue part. But how would you go about relieving them? Well, there are two obvious methods that come to mind. You could allow the robot to either analyze the victims and give some state to their condition, or you could allow the robot to move by itself through the environment, as we've talked a bit about before. Now, of course, the optimal solution would be for the robots to both navigate the environment and analyze the victims and do everything on their own, and just leave the robot operator sitting in an armchair eating popcorn. But it's been shown that robots are not great at recognizing the state of the humans that need rescuing. So instead we'll be focusing on autonomous movement, since this seems a plausible near future subject. Now, what this means is that the robots move completely on their own through the hostile environment. And it's actually already been shown that robots are often not better than the human operators at navigating through disaster areas. But this also needs to be developed. As I talked about before, it's not just about the robots moving on their own, but also about suggesting a good path for humans. Now, one way in the swarming example could be drawing parallels to the ant system algorithm, where the robots might leave markers for each other, saying that, okay, I already went this path, how about you go another path? Or this path was too dangerous, let's just ignore it altogether. And another key feature is optimized interfacing, since the operator needs to be able to interpret these feeds from all the swarm robots. So let's imagine a scenario. Say we have 40 robots swarming into a building, and the operator sits by his computer and he has 40 camera feeds, one for every robot. Now, let's say 10 of these, they just crash and burn. Their camera feeds go blank, they're out of the picture. Say 5 of these find humans in need of rescue, but also find a safe way to these humans. Say that they mark their camera feed with a yellow box, and well, basically the operator can see this yellow box and say, oh, these humans need rescue, go in, save them, no problems. And then one robot might find a human who's behind some blockage that can't be reached directly. So let's say he marks his camera feed with a red box. Then that might be prioritized by the robot operator. Now, what should the robot do once it has found this victim with the red box? Well, one solution might be that it flies back and checks out the blockage, and either just shows the camera feed, allows the human operator to decide on some action. But in the long run, it will of course be preferable if the robot itself analyzes this blockage and just sends back a suggestion on what to do. Now, another important thing is efficient exploration, and this is expanding a bit on Amanda's previous example with the human going in and the robots swarming around it. Let's consider that example and factor out the human and just use robots. So what I would be referring to this as swarming, but don't confuse it with the particle swarm algorithm. Instead, what I mean is that a multitude of robots swarm into a building, moving in without collisions, but everyone moving towards some common goal, sort of like the particle swarm algorithm. Now, this kind of behavior requires an advanced autonomy and communication between the robots. They need to communicate some sort of branching point in the swarm. Say, for example, we run into a three-way corridor. The robots need to decide that 1/3 goes that way, 1/3 goes the other way, and 1/3 just continues ahead. Now, to make these calculations, you would require a fairly powerful processing unit. So there are a few ways to go about this. You could either have the robot doing all the calculations by itself, incredibly heavy for one robot, making them very expensive. You can have a single processing unit, a hub back at the robot operator, and just send the data back and forth. Of course, a loss of contact would result in 40 robots crashing and burning. Then you could just use cluster computing, where all the robots aid each other in calculations. But of course, that also increases the cost of each unit. So how to go about this? Well, the future will tell. Now, another important thing, since there are so many robots and it's virtually impossible for the operator to keep track of all of them at once, is a very reliable life sign detection system. And this might be achieved through facial recognition or measuring body heat and other things. Now, what should it do once it has determined that it has found the victim? Well, one example might be like before it goes back and analyzes blockages. But if there aren't any blockages, what should it do then? Well, one idea would be to stay with the victim and ping its location on a collective map used by both the robots and the rescue personnel. But this would require very precise location announcement. Say, for example, that it has found the victim sitting leaned against a wall, and it pings its location, but its map is not precise, so it shows its ping on the other side of the wall, sending the rescue personnel into the wrong room. Now, we can't really have that happening. So I imagine some of you might be thinking about GPS or RCM or some technology like that to give a precise location announcement. But we believe there's an even simpler solution. Instead, you could use an average map from all the robots that have swarmed into the building and synchronize this map with maps used by the rescue personnel. That way, all the robots and all the rescue personnel will be using the same map. And it's not really important how exact it is, since everyone is using the same map. Now, I would believe that through implementation of technology like this or similar ideas, it will be possible for a swarm to go into a building, map it out entirely, ping out the location of each and every victim with varying degrees of severity, indexing severity of blockages, severity of condition, and just returning a list of which victim to take in the order of which to take them. And allowing for a very smooth and painless process in extracting injured humans. So thank you. I would like to give over to Erik.
Thank you. So we're reaching the end of the presentation, and it's time to give the promised summary. So what is search and rescue robotics? Search and rescue robotics is the use of robots where it's unfit to use humans, or rather more beneficial to use robots. And one of the benefits being that humans and robots are good at doing different things. Like the snake that could wiggle itself through small crevices, like Amanda was talking about, or the swarm robots that could map out a big area, and then the humans could come in and rescue the persons. We also addressed the question of manual versus autonomous steering of the robots. Autonomous having the benefit of being independent and fast, requiring a minimum of human interaction, while also having a hard time distinguishing different things. So the solution is, again, to work side by side and use the strong points of both humans and robots. And to use fully autonomous robots is probably quite far away. It would require a lot of computing power. If you remember the video Matthias Bade showed in his course, where there was a camera in the car. The camera could distinguish between different cars and persons. We probably need something like that in each of these small robots. I think they used a PC that's moving, that's the thing. So if you mount a big PC on each robot, it would require a lot of energy, electricity, and also computing power. So maybe in the future, we'll have better batteries and better computers. This could be reality. We could have Terminators walking around the streets. I think we'll have to wait some time. But in the meantime, I have I can recommend two names to look up. So the first one is Robin Murphy, the woman who wrote Disaster Robotics, and she seems to be like a really big shot in this business. I haven't read the whole book, but what I have read is very nice. It gives an introduction to the subject and what has been done so far. Really, it doesn't really focus on complexity that much. It's mostly using a single robot at each time. The other name is Vijay Kumar. He doesn't necessarily work with search and rescue robotics, but he's has a lot of cool robot projects going on. So there's a lot of, you can read about his projects and his videos on his webpage. I really recommend it. He's at Penn Engineering in Philadelphia. But also quite a big name. All right, and we've also found, this isn't really SNR yet, but found a couple of do-it-yourself guides on the internet if you want to build your own swarm boss. So this one is from instructables.com, and you build it from a computer mouse. You can see the back part here, and some plastic that can go around. And it's $16.50 for one, approximated dollars, American dollars. And also all the documentation for the kilobots is available online, and they're estimated at $20 each if you buy 1,000, and $50 each if you buy 100. So if you have some time and money to spare, you can build an army of kilobots. And that's all. Thank you for listening.